Good morning, class, and welcome to this lesson on Modern 5, the Compton effect. Today we will be able to describe how a photon collides with a particle. So, um, thinking about this discussion of modern physics, talking about the underlying theme of modern physics is this concept of wave-particle duality, the fact that waves and particles can exhibit both particle and wave-like behavior at the same time. So far we've discussed the photoelectric effect, and now we're going to discuss the Compton effect. This would be like a step two in the proof that waves and particles can exist in both states, as a particle and as a wave. So the Compton effect is pretty simple. Well, maybe not simple, but I think it's a simple concept to understand. What this guy figured out, Arthur Compton, what he figured out was that when an X-ray photon, a photon was shone upon a particle, an electron at rest. The electron, it hit it. The electron was sent into one direction, and the photon was sent into a different direction. And what was interesting about this was that these photons had different wavelengths. So this one had a certain wavelength, and this one had a different wavelength. We'll call that wavelength prime. Okay, so these are two different wavelengths. And this picture, this diagram of a photon hitting a particle should look very familiar to you. It looks pretty much like a collision between two particles or between two objects, just like we discussed in momentum. And because it is. And so what happened was we have the energy of a photon. This would be this photon right here. This is the before the collision. This would be before the collision. And then afterwards, after they hit, we have the energy of the scattered photon. I'm going to call that F prime because this is now different, remember? And I can relate F prime and wavelength prime. These are synonymous because we know that the speed of light equals wavelength times frequency. So if wavelength changes, frequency also changes. So these two I can use those interchangeably. Plus the kinetic energy of the recoil electron. So basically, what Compton figured out was that photons have momentum. Momentum typically being attributed to a particle, P equals mv. Well, before this, no one would have said that because in order to have momentum, you must have mass. But particles also, or excuse me, photons, energy also has momentum. Okay, I don't think you need to memorize this equation right here. I'm just showing you the logic behind it. So what Compton did was he combined this equation. He combined the conservation of momentum equation, conservation of momentum, which I'm sure you remember, M1v1, M2v2, that kind of stuff. So he combined these two ideas, and what he found was that the momentum of a photon, P momentum of a photon, is equal to the Planck's constant over the wavelength. So now what we have here, according to the Compton effect, is we have an ability to relate two different things that were never relatable before. We have wavelength, which was a particle thing, which is a wave thing, energy thing, and then we have momentum, which is a particle thing, and now we're able to take these two and combine them together. Just like we did with E equals mc squared, we had energy and mass, and put those two together. I mean, this shouldn't have been done, but now modern physics, we are able to see that these two are equitable. And so I'm just going to cover this real quick. Compton then found that the difference in wavelength prime minus wavelength, so this is the difference in wavelength, is equal to h over mc minus 1 minus cosine theta. This is the angle that they are deflected. You don't need to know this equation for this class in particular, but I just want to share that with you in case you do for your classes. So that's it. That is the Compton effect. The Compton effect is a demonstration that photons have momentum. based off this picture right here. When a photon hits an electron, it collides, and some of that energy is transferred over to the electron. Some of it is lost. We have a new wavelength from the new, from the post-collision photon.